This is question 23 from section 2 of the 2007 BMAT. In this question we're told we have an artery. It's got cross-sectional area A. It's got a length x millimeters. We're told it takes big T seconds for a red blood cell to travel from one end to the other. We're told the flow rate is big V milliliters per second. And we're asked to find the cross-sectional area A measured in millimeters squared. So if you want to have a go at this question yourself, pause the video now. Okay, so there's a couple of things we have to deal with here. One is knowing what flow rate is all about, and the other is dealing with the units, because this is in milliliters and this is in millimeters. So let's just think about flow rate first. There is a formula you can use here that I'll discuss at the end, but if you don't know that, we can do this from first principles quite quickly. So let's discuss what's happening and why. Imagine we start with our entire lengths of artery filled with blood at t equals 0, so at the start. What's happened after t seconds? Well, all the cells that were at one end, all the blood at one end, has got to the other end. So that means this whole artery's worth of blood has now flowed through. So big T seconds is the time taken for one artery's worth of blood to flow all the way through. So we can say that every big T seconds we have one artery's worth of blood flowing through, and that tells us about the flow rate. The flow rate is just the volume we move through in a particular period of time divided by the time. So the volume of stuff flowing through per unit time. So now we can work out the volume of one artery's worth of blood because we know the length, and well, we have a letter for the cross-sectional area, so it's going to depend on that. And we have big T, so that will give us an expression for this side, and we have an expression for this side, and we can rearrange for that area A. So let's try and do that. Okay, here's all the information we're starting with. And we do have to be careful about the units here. So let's try to plug in the letters we have into here and rearrange for A, but we'll take into account the units all the time. Bear in mind, if you look at the answers, a lot of them have powers of 10 in, so it's likely we do have to take that into account. So let's think about what 1 litre is. 1 litre is 1/1000th of a cubic metre, or 10 to the minus 3 cubic meters. So I'm going to convert everything to meters basically because it's the standard unit, and we know the relationship between millimeters and meters. And that means the flow rate, well, it's 1 milliliter per second, so that's 1/1000th of that. So it's going to be V times 10 to the minus 3 liters per second, because this is 1/1000th. And then we convert the litres into cubic metres. That's another lot of 10 to the minus 3. The powers add, so we get 10 to the minus 6. And now we have to think about the right-hand side. So T is fine, but we need to think about the volume of the artery. And we note that X is measured in millimetres, and we're looking for A in square millimetres. So here we know 1 millimetre is again 1/1000th of a metre, 10 to the minus 3, and 1 square millimetre is 1 millimetre times 1 millimetre, so we square this factor. This is also an instance of the square cube law. We square this factor, and that gives us 10 to the minus 6. Again, it's like having two factors of 10 to the minus 3, and the powers add just as they did here. So if we plug those in, the volume is our area. So here I'm going to measure this in meters. So it's A times 10 to the minus 6 square meters times X times 10 to the minus 3 meters in length. And again, we've got these factors multiplied together, so the powers add. So we get the A times the X and then 10 to the minus 9 cubic meters. So if we plug those into our equation here, on the left we have our V times 10 to the minus 6 from here, and on the right we have AX times 10 to the minus 9, and now we divide by T, and everything is in terms of meters and seconds. So now we just have to rearrange for A. So if the powers of 10 weren't here, we'd just bring across the t and divide by x, so we get vt over x. What happens to the powers? Well, what we need to do to cancel this is to multiply by 10 to the 9. If we multiply this by 10 to the 9, the powers add to 9 minus 6 is 3. So we get our vt over x, and then we have an extra factor of 10 to the 3. And that turns out to be option E. So that's the answer. So we've got to the answer. I will just discuss quickly a couple of other methods of approaching the question. One small thing is to do with converting units. So one thing we could have done instead would be to directly convert millilitres to cubic millimetres. So we start off with 1 cubic metre is 10 to the 9 cubic millimetres, and 1 litre is 1,000th of that, so we decrease the power by 3, and then a millilitre is 1,000th of that, so we decrease the power by 3, and we get this value, and we could write everything in terms of cubic millimetres instead of in terms of cubic metres. And the other thing we could talk about is how to get the equation for the flow rate, or rather a simpler equation you can use to find the flow rate or to give an expression for the flow rate that you can just memorize instead of having to work out in the way we did. So we were saying at the start that the flow rate is the volume flowing through per unit time, but we can also, well, we also found that's the cross-sectional area times the length over time. This is if we have a uniform cylinder, but that's how any question you see is going to be presented. And one thing we note here is if we have the time, as in this case, to flow along the complete length of the artery, then the speed that the liquid, in this case the blood, or it could be any other fluid, the speed the blood is flowing at is just the length of the artery divided by that time. So that means the formula for the flow rate is cross-sectional area times the speed of the fluid, as long as we have a constant cross-sectional area and a constant speed. But that's, again, how most questions will be presented. So if you like, you could remember this formula for the flow rate, and then in this particular question we could have found the speed from length over time and approached the question that way.